Okay, congratulations. You made it to the third and final video of the how to deal with second order ODEs. Hopefully you're not too hungry looking at all these delicious chicken wings in the background. Man, I need to get so by the way, in the middle, uh, this is kimchi coleslaw on the left hand side there in the middle. It's delicious. In the very center is some pickled daikon radish, which used to be unlimited. You used to be able to get as much as you wanted, but then I think I ruined that for humanity, and now they only give you like one portion of it. And on the right is some kimchi, it looks like, which I have not tried, but the kimchi coleslaw is great there. I'm sure the kimchi is also good. But the wings, ooh, the wings are fantastic. Okay, yeah, so we're going to talk about another method of how to solve second order ODEs, and the method is going to be called the method of variation of parameters. These are such scary names. Undetermined coefficients, variation of parameters. Yikes, lots of big words. So first of all, when do you use these methods? You remember before when we talked about first order ODEs, sometimes you use, if the functions were homogeneous, and then we had a certain technique to use. We had Bernoulli equations, which we use a different technique. We had that other weird method that we could use where if, like, you had a linear function of x and y. So there's a lot of like strange methods to use. Here there's only really two important ones for now, at least. The one that we just did, the method of undetermined coefficients. We use that if this function on the right hand side is made up of nice things like polynomials, exponential functions, or linear combinations of sine and cosine. Nice functions. If you have anything else, like, I don't know, quotients, or I don't know, just all, I mean, really anything else. There are a lot of gross functions out there. Then this other method that we're going to talk about right now, this method of the variation of parameters, might just save the day. So let's talk about how this method works first. So just like in the last problem, you're going to find the homogeneous solution first, which hopefully is easy by now. You've been doing this for 2 whole videos. And then now things get a little strange. So you take your homogeneous solution that you found, and you replace your constants. So you remember you've got your constants C1 and C2. Those are just numbers. But we're going to replace those with actually functions. It says here to replace them by variables, but it's actually more general than that. We're going to replace them with functions of x. So instead of C1 times Y1 plus C2 times Y2, I'm replacing it with U1 and U2, where U1 and U2 are not constants, they are functions of x. Seems crazy. So this is like our new ansatz, I guess. Now things get really weird. Whoever came up with this is quite brilliant. So what you're going to do then is there's a system of equations that you're going to solve. Again, this is just kind of rabbit out of a hat. There's some real kind of magic going on behind the scenes here. I might try to see if there's a way that we could prove this in the problem set, but I imagine the proof is pretty challenging. But here's the system for how you find U1 prime and U2 prime. It's given by this weird system where it's U1 prime times Y1 plus U2 prime times Y2 equals 0. So essentially you're just only taking the derivative of the U terms. That's the first equation in the system. The second equation in the system, you're putting primes in everything. You got U1 prime times Y1 prime plus U2 prime times Y2 prime. It looks kind of like a nasty product rule, but it's not. I mean, it's like the wrong product rule. I'm just taking the derivative of everything, and that has to equal f of x. That has to equal your function on the right-hand side. You solve that system for U1 prime and U2 prime. Sometimes it's going to be, I'm going to make sure that it's generally easy for you, that the algebra is not too bad, but I mean, it could be a nightmare. It could be really, really hard to solve that system. Once you found U1 prime and U2 prime, then you just integrate. You just take the antiderivative to find U1 and U2, and that's your missing parameters. So we're varying the parameters here. Instead of the parameters being constants, they're now functions. And we're finding these functions by using this really kind of mysterious method. And then once we've got that, once we've found U1 and U2, that's going to give us our y sub p. And if we add that to our original homogeneous solution, y sub h, that's going to give us our general solution. So this looks like insanity. Let me please try and illustrate this with some examples here. So the first example I want to show you is this one, where the left-hand side looks like, easy. It's stuff that we've been dealing with all along. The right-hand side looks awful. The right-hand side is not a polynomial. It is not an exponential function. It is a combination of those two things. And it's a terrible combination. It is a quotient of those two things. So again, we treat the homogeneous case first. So the left-hand side has a characteristic equation of m squared minus 2m plus 1, and that, of course, has a double root at 1. And so because it has a double root, I use this formula where it's c1 e to the x plus c2x e to the x. It's the same root twice. Okay, so that's y sub h. Hopefully that's clear for everybody. That's, again, going back 2 videos now, just solving a homogeneous equation. Now comes the fun. We replace those c's with u's. So, okay, this seems kind of weird, but this is the method. This is how it works. So I replace C1 with U1, and I replace C2 with U2. And the difference here is that C1 and C2 are constants. U1 and U2, I can't reiterate this enough, are functions. They are functions of x. Maybe I should have put U1 of x there, but the notation gets a little cumbersome. Okay, so then we set up this system of equations, which is just terrible. So it's U1 prime times y1. y1 here is e to the x, right? So let me kind of circle some things here. So e to the x is what's going to, oops, there we go. E to the x is what's going to be coming in there, and then x e to the x is what's going to be coming in here. So the system of equations, again, is u1 prime times y1 is e to the x, plus u2 prime times y2, and y2 is x e to the x. That has to equal 0. The second equation in our system, maybe I should put brackets around over here so you can see that this is a system of equations. The second thing in the system is u1 prime times y1 prime. So what's the derivative of e to the x? Of course, it's e to the x. So that's where this, let me do it, use a different color. This e to the x right here is the derivative of that e to the x right there. We add that to u2 prime times the derivative times y2 prime, right? So the derivative of y2. Again, this thing right here that I just put a blue box around is y2. y2 prime, then, we have to use a product rule, and we get e to the x plus x e to the x. Okay, so that's u1 prime times y1 prime plus u2 prime times y2 prime. And that has to be equal to the right-hand side of our equation. So that's this thing right here. Okay, hopefully we can follow all these. So maybe I should be putting arrows. I don't know. This is just so bad. So this goes here and here. This goes here and here. Everything's all over the place. But you do all that to find your system of equations, which again is these bottom 2 equations right here. So you do some algebra on this. I think what I did here is I took the second equation and I subtracted the first equation. And if you do that, you get a lot of cancellation, right? The u1 prime e to the x cancels, the u2 prime e to the x e to the x cancels. So you're just left with u2 prime e to the x equals e to the x over 2x. And if you do a little algebra on that, you'll see that u2 prime has to be 1 over 2x. Take a minute or two to make sure that makes sense to you, but we're just doing some fancy algebra. We're doing some elimination. I take equation 2 minus equation 1, and I'm getting that u2 prime has to be 1 over 2x. If I take that and plug it into the top equation, that 1 over 2x, if I plug that in for u2 prime, then I can solve for u1 prime, and I'm getting that u1 prime has to be negative 1/2. Again, verify all this, but I'm just solving the system of equations. This system right here. These two equations right here. I'm finding the simultaneous solution, right? I'm finding u1 prime and u2 prime that solve both of those equations. Okay, and so that was I forget what step we're on now, 3, I guess. So step 1 was find the homogeneous solution. Step 2 was make your ansatz for yp. Step 3 was to set up the system and solve it. That's what we just did. And now step 4, we integrate. We take the integral of u2 prime and u1 prime so that we can figure out what u1 and u2 are. u2 is going to be, I guess it's technically just 1/2 ln of x, but I'm taking that 1/2 and moving it inside as an exponent because I like to be fancy like that. So hopefully this is clear for everybody. The antiderivative of 1 over 2x, right, is 1 over 2 times ln of x. ln of absolute x, but whatever. But the 1/2, you remember your log properties, can go inside as an exponent. So this becomes ln of x to the 1/2, which means ln of root x. That's some fancy algebra and precalculus action going on there. So u2 is the natural log of root x. u1 is, I mean, that's the antiderivative of a constant is just linear, so it's negative 1/2 x. don't worry about putting any plus c's on the end. Just find the antiderivative with no constant term. Okay, and then, oh boy, so low here. So we found now, so u1 is negative 1/2 x. I'm going to take that and I'm going to plug it up here for u1. Boom. u2 is ln of root x. I'm going to plug that in right there for u2. And that's going to give me what y sub p is. All this work to figure out what my other solution is, y sub p. So if you plug that all in, that's where this business is coming from. That's what's coming from yp, right? And then the first thing there, the c1 e to the x plus c2 x e to the x, that's your yh, that's your homogeneous solution. So by simply adding those two equations together, we get the general solution y. Ooh, yikes. And again, last step is to always check these things. You know, take a derivative if you dare. It's going to be so bad. You have to use like a triple product rule on that last term. It's so gross. But take a derivative, take a second derivative, plug everything back in, and it should satisfy the ODE. It's just awful in every way. Let's do one more example because these are quite tedious. This one looks relatively nice, but it's, as you'll see in a moment, not at all. Y double prime plus y is equal to tangent of x. Looks so straightforward, looks so simple. Well, first of all, the characteristic equation here is what? M squared plus 1 equals 0. And the only solutions to that are plus or minus I, which is very disappointing. So this means that alpha is 0, right? The real part of this is 0, and the imaginary part is 1. So the general solution is, as you'll recall, c1 e to the alpha x, but alpha is 0, so that's gone, times, cosine of the real part is 1, so 1x, and then plus c2 sine. So that's exactly where that's coming from. The homogeneous solution is c1 cosine of x plus c2 sine of x. Hopefully that's clear. So then our y sub p, again, all you do is you replace the c's with u's, but c1 and c2 are constants, they're just numbers. u1 and u2 are functions of x that we are going to try to find out. We are varying the parameters. Okay, so then we set up this system. u1 prime times cosine plus u2 prime times sine has to be equal to 0. And then if I take derivatives of everything, I'm going to get u1 prime times negative sine of x. I put the negative in front, but u1 prime times the derivative of y1 would be negative sine, plus u2 prime times the derivative of sine, which is cosine. And that has to equal f of x, which in this case is tangent of x. So again, let me maybe draw some arrows here with where everything's coming from. So cosine of x goes here, and the derivative of it goes here. And sine of x goes here, and the derivative of it goes here. And you've always got the primes over the u1 and the u2s. Make sure that the first equation equals 0, and the second equation equals whatever f of x is. So there's your flow chart, essentially. Okay. Whew. So I did the dirty work for you here. I guess this one isn't too bad. I guess what would we do here? Multiply the top equation by sine of x. Multiply the first equation by sine of x and the second equation by cosine of x, and then add them together, and you see the first terms will cancel. And then you've got this nice sine squared plus cosine squared, which is 1 action going on. It gets really nice. So just go through this yourself. Go through, remember your trig and your algebra, and what you'll see is that u2 prime has to be sine of x. Take that, plug it back into either equation, and you'll see that u1 prime has to be cosine of x minus the secant of x. Oh, so sorry, but that's how things happen sometimes. Okay, so now we integrate to figure out what u1 and u2 are. u2 is easy, and the integral of sine is negative cosine. u1 is a little bit harder, so the integral of cosine, of course, is sine. That's easy. But the integral of negative secant, I don't know if anyone remembers this. It's always in like the front cover of your textbooks. But the integral of negative secant is negative natural log of the absolute value of secant x plus tangent of x. Look it up, if you memorize that for some insane reason, that's awesome. But that is what the antiderivative of secant is. The antiderivative of secant is ln of absolute secant plus tangent. It's crazy. Okay, so we found our u1, we found our u2. We take those, we plug them back in up here for u1 and u2, right? And that's going to give us y sub p. and we add all these functions together, and then we found that the solution to, remember our differential equation looks so easy, it's just y double prime plus y equals the tangent of x, and the solution is absolutely putrid. It is c1 cosine of x plus c2 sine of x minus, this last term is just insane, cosine of x times the natural log of the absolute value of secant plus tangent. Just looking at this problem, nobody would ever guess that, but there it is. That is the solution to that differential equation. Check it to be sure. Take two derivatives of this thing. Somehow, it looks awful. Add it to itself, and you should end up miraculously with all sorts of cancellation with just tangent of x. Kind of crazy. Okay, so I hope you've enjoyed exploring this magical world of second order ODEs with me. Let me know if you have any questions. Good luck. Have fun. See ya.